Hi, I'm Mu and come from Carnegie Mellon. Today I'm going to talk about the primary server. It's a distributed system optimized for machine learning tasks. This is a joint work with my colleagues from Carnegie Mellon, Baidu, and Google. When I want to go OSDI's website, what I usually do is that, okay, I query OSDI in Google and get the link from Google. And did that some time ago, but I find something different here. Because the first result is an ad. That means if I click this link, yes, I did, the advertiser, who's probably a USENIX, will be charged by Google. So, sorry about that. But from Google's point of view, if Google wants to make more money, it should display the ad the user would like to click. But we don't know what the user behaviors when selecting these ads. So what Google wants to do is that you need to predict whether or not the ads will be clicked. That becomes a machine learning problem. So machine learning is concerned with systems that can learn from the data. Typically, the more the data, the better the accuracy. So this figure shows how the data sizes increases for the previous ad click prediction problem over the past years. On 2010, we used less than 10 terabyte data for this task, but this year, this training data goes to more than half petabyte. And because the accuracy of this machine model directly affects the revenue, so it's no surprise the annual revenue of this company grows increasingly. And in this talk, I'm going to show the result on the largest data set using 1,000 machines. This is by far one of the largest machine learning tasks we know. Okay, before we go, I would like to first briefly overview of the machine learning task. The first step is that we connect some raw data. In the previous example, it's just some ad impression logs. We get this data, we do feature extraction, we get the training data. And then we input this training data into a machine learning system and get the machine learning model we want. It's typically just a list of key-value pairs. And these pairs can be used to predict the future. Let's zoom in what is the training data looks like. It's typically just the example by feature matrix. It fits into the big table data structure. On the ads example, each row is an ad impression, each column is a feature. It could be a query OSDI, or could be a word in this ads, or could be my user identity. So because we display billions of ads each day, and we have billions of users, so this matrix goes billions by billions size. This size is not uncommon. A typical industrial problem, you have hundreds of billions of examples, tens of billions of features. This training data range from 1 terabyte to 1 petabyte. And we often run it over 100 to 1,000 machines. In this talk, we focus on the machine learning system. We will present the primary server. It scales to these problems, and it provides efficient data communications. It is fault tolerance and easy to use. Okay, so let's first discuss how to scale to these problems. Our first problem is that the training data is too large to be fit into a single machine. What we can do, we can partition this training data into several workers. We just say it's worker machines. What about the model? It's a list of key-value pairs whose size is at least as the number of features you have. That also could be tens of billions. Similarly, we can partition this model into a bunch of machines we call server machines. So after partition, we can do the training. There's two types of data communication between these machines. One is that a worker can push the local computer result into the servers, or a worker can pull the new result from the servers. So this whole architecture we often refer as a primary server architecture. Given this architecture, let's show a concrete example how to run the distributed gradient descent in it. For simplicity, I just assume there's just one single server machine, and the training data have been partitioned into two workers. The first step of this algorithm is that each worker pulls the working set of the model from the server. Now we can start iterate. The first step is the worker compute the gradient using its working set of the model and the local training data. Next, the worker push this gradient to the servers. After aggregate this gradient, the worker update this model, and finally, the worker pull the updated model from the server. So now we finish one iteration. We can run it again and again until we get the model with the accuracy we want. Next, let's focus on how to run the previous example efficiently. The main challenges comes from the data synchronization between all these machines. This is because all these workers need to read and write the huge shared model frequently. This results in huge data communication traffic. And also, there's global barriers between iterations. These global barriers are expensive. Our goal here is to reduce these synchronization costs. Before showing our solution, I would like to first introduce the concept of a task. A task is similar to a remote procedure call. It could be a push, could be a pull, or any user-defined functions, such as one iteration we discussed before. Traditionally, there's a execute after finish dependency between tasks to guarantee the data consistency. For example, on the previous gradient descent, each iteration has two stages. One is the CPU-intensive stage, you compute the gradient, and there's a network-intensive stage, push the gradient, pull the result. So if there's a dependency here, we should start the next iteration after the previous one finished. However, this is not efficient because the CPUs are idle in the network stage. What more we can do? Well, we can execute this task asynchronously. So still on this example, we can start the next iteration, compute the CPU stage immediately after the CPU stage of the previous one finished. So we can maximize the CPU usage here. However, it introduces some data inconsistency because the new result from the previous iteration have not been pulled back yet. This data inconsistency is a trade-off between algorithm efficiency and system performance. The best trade-off depends on a lot of factors, such as CPU power, network bandwidth, algorithm properties. We believe there's no single consistent model fits all these machine learning tasks. So instead, primary server provide flexible consistent model using the text dependency technology we discussed before. For example, we can place a text dependency between two sequential tasks and get the sequential consistent model. And then we can do nothing here, so we get the eventual consistent model. Between these two extreme cases, we can have a bounded delay model. That is, a task can be parallel with resting tasks. However, it should wait very old one finished. So the delay here just controls the amount of data inconsistency between machines. Now let's show some result using the add-click prediction experiment. So we first run this experiment using a sequential consistent model. The advantage here is that we get the result as if we just run on a single machine. However, we pay the cost that half of the time is wasted on waiting because of this consistent model. Now we elect this consistent model by allowed delays here. What we can see is that the computing time slightly increases with the delay we have. This increases is because of the data inconsistency slows down the algorithm. However, it reduces the waiting time a lot. In these experiments, the best trade-off here is the A delays. And the task dependency controls data consistency between tasks. We can do more. We can do fine-grained control of the data consistency using the user-defined filters. It does so by selectively communicating key-value pairs. For example, we designed a KKT filter. It only pushed part of the gradient if this gradient would likely to affect this model by examining the optimal condition of the machine learning algorithms. We applied this filter to the add-click prediction task, and we found that during running, more than 95% of keys are filtered. So we save a lot of network traffic here. And we have more technologies such as key caching and value compression. So please read for the paper for more details. So now I would like to move to the fault tolerance part. To motivate this problem, we connected the machine learning job logs in a 3-month period in the production data center. We classify these machine learning logs into 3 categories by their machine time, and we report the average failure rate. For small tasks, more than 6.5% of jobs are die during running. And this number goes to more than 13% for medium-sized jobs. However, for real large jobs, every 1 out of 4 jobs are failed during running. So a machine learning system should be fault tolerant. In this talk, I mainly focus on how to do the fault tolerance on the server machines. First, a model is partitioned to server machines by using the consistent hashing. And by default, the data are replicated by the chain replication. So for example, if a worker sends the data to a server, the server replies this worker only after the data has been backed up on the another server. So this chain replication is consistent, and it is safe because you can run it for all of the machine learning algorithms. However, it results a lot of network traffic. But for some particular algorithms, we can use aggregation to reduce this backup traffic. Remember, for the gradient descent, each server machine needs to aggregate all this gradient from the workers. So we can, rather than back up every individual gradient, we can just back up the aggregated gradient. For example, if here we have 2 workers and they want to push X and Y to the server, what the server does is that you first wait both X, Y are ready, aggregate X and Y and back up it, then you reply the workers. So in this case, we can reduce the backup traffic. However, it increases the latency because the server needs to wait all this worker finished. But we can fix it by using the relaxed consistent model we discussed before. And I also would like to mention that we implement this aggregation by efficient backward clock. Please refer the paper for more details. Now I would like to discuss how to make the system easy to use. The key observation here, the machine learning algorithms lack mass objects, such as the sparse vectors, matrices. So we can implement this object by using the key-value store. But rather than provide the standard key-value store API, such as single key read and write to the users, we allow the users to use this object just as mass object. So it's good for the programmer because it makes them easy to implement the machine learning algorithms. And it's also good for the system because there's much more optimization opportunities to take advantage of these data structures. For example, if we want to implement the computing gradient logic on the add-click prediction task, what we can do is that we just use the provided multi-threaded linear algebra operators between the local training data and the global shared model, so that we can write this function in just a few lines of code. Now I would like to move to the evaluation part. We evaluate this system into large-scale machine learning applications in different internet companies. So the first application is the predict ads we have been discussed before. So we use the Sparse Logistic Regression as the machine learning applications. We use 2 systems in production as the baseline. System A and B using different learning algorithms, but use the same sequential consistent model. We implement the algorithm used by system B in primary server, but relax its consistent model into bounded delay and the KKT filter. Because the primary server provides a user-friendly function, so we can implement the same algorithms by reducing the lines of code to 30,000 to 300. To evaluate this system, we collected more than 600 terabytes of real ads data. It contains 170 billion of examples, 65 billion of features. We evaluate this system using 1,000 machines. This is about 60,000 of cores. Here we show the convergence result. The x-axis is the runtime. The y-axis is the error of this model. So this is a result for system A. As the time goes, what we can see is that the accuracy of this machine model gets better. And we stop this system if we get the model with the accuracy we want. System B gets the model with the same accuracy much faster than system A. So system B outperforms system A. Primary server outperforms system B because even that they use the same learning algorithms, and even with less lines of code. The reason can be clearly seen in this time decomposition figure. System A uses a sequential consistent model, so about 30% of the time is Western weighting. And this number goes to more than 50% for system B, because system B is a much larger number of global barriers than system A. Primary server use slightly large computing time than system B because of the data inconsistency slows down the algorithms. However, it reduces the waiting time a lot. As a result, primary server uses half of the time than system B. Our next application is topic modeling, often referred as LDA. So we implement a gradient descent uses an eventual consistent model in the primary server. It's similar to the algorithm used by Andersen. And to evaluate this system, we collected 5 billion of user logs, and we grouped these users into 1,000 groups based on the URL they clicked. So these groups are user interest group. For the result, we also show the time versus the error of the model. We first show the result using 1,000 of machines. As we can see, this model converges after about 50 hours. And what if we increase the number of machines to 6,000? What we can see is that we can get a model with the same accuracy much faster than 1,000 of machines. It's roughly 4 times speed up here. Why we can get so good result? This is because we use the eventual consistent model. So that's almost a low waiting time here. Finally, I would like to briefly review the related systems. So we just compare the largest experiments they run before. The x-axis is how many CPU cores have been used. The y-axis is the model size. First, there's several systems. Reef, ML-based on Spark, Layard, can run logistic regression. This is a similar machine learning task comparing similar to our as-click prediction task. However, they use much less computational power. They produce model with much less size. And also, GraphLab and Yahoo LDA can run large-scale topic modeling, but still far much smaller than the experiment we run here. There's deep neural network system, Adam and Disbelief, they focus on the model goes to deeper, but we focus on model goes to bigger. And I believe the future is for model goes to deeper and bigger. Well, in conclusion, so in this talk we present the primary server is scaled to the industrial machine learning problems because we do data parallelization and the model parallelization here. It's efficient for the data communication. The key insight here, we trade off the data consistency for system performance. It is fault tolerance by using consistent hashing and by aggregate chain replica. It is easy to use because all these objects are mass objects. So it's very easy to write machine learning programs here. And we show the evaluation in the 2 largest machine learning applications we know so far. Finally, the code will be available at primaryserver.org. And thank you. I would like to take questions.
Okay, we have some time for questions, if people have any. Here's one. Here's 2.
Okay, Mingjie from NYU. And according to your experiment, that the LDA seems to be tolerate the eventual consistency, right?
Yeah.
So yeah, this seems to be interesting because there's a trade-off between the algorithm accuracy and also the system consistency model. Mm-hmm. So is there any quantitative or any results of that? No.
Well, this is a good question. So the question is that how different algorithms for how the incentive of the algorithm to the data inconsistency. So it's really depends on the algorithm properties and the data. For example, the correlation on the training data and how the algorithms sequentially. We have some theoretical result, but not in this OSDI paper because it's not a good idea to put any equations on the paper. So we have a NIPS paper to show that for some algorithms, even using the very relaxed consistent model, for example, the bounded delay for the user-defined filter, you can still converge, guaranteed convergence. And you could be slightly slows down, and we can have some quantitative result. But it's a theoretical result, it's an upper bound. In practice, we just tried.
Okay, thank you.
Kim Keaton, HP Labs. So the notion of bounded delay has been explored recently by some of your colleagues at Carnegie Mellon in the Lazy Tables project, and I was just wondering if you could say a little bit about how your work differs from theirs.
Oh yeah, so the bounded delay has been discussed on the machine learning community for several years. For example, Alice Smola's paper on 4 years ago, the slow learner fast. For here, the bounded delay is just one kind of consistent model we use. So we can use the task dependency to implement any consistent model you have. And we can also do some fine-grained control of the consistent model. We use the bounded delay model for the ad-click prediction, but we use different delay model for different applications. So I think comparing to lazy table, we allow much more flexible consistent model, and it's more general framework.
Hi, Naveen Duchen, Microsoft Research. Very cool work. I was curious that in your accuracy graphs, you seem to have cleverly, hidden the quantitative numbers. So can you tell us some intuition of what is the degradation on a relative scale, say perhaps, or even absolute numbers, in terms of your error change for your different schemes?
So which result, I think?
I mean, all of your accuracy graphs have hidden y-axis.
Oh, you mean this one, for example? Okay, the y-axis is the object value you have. So because I'm afraid people may be not familiar with the object value, so I just use the arrow here. So for example, for the ads here, this is a convex optimization. So there's a unique solution. If we get this accuracy we want, if we get the object we want, we guarantee that you get the exact solution you want. And it is directly related to the accuracy, the final test accuracy of the machine learning model you have.
Is there a quantification of what that accuracy is?
Yeah, sure. We have the more details on the paper, but for this talk, I just use a simple y-axis here.
Okay, thank you. Let's take it offline.
Sure.
Let's thank the speaker again. Great talk.